The road to Koo, Belgium, stretched empty beneath a heavy grey sky on the morning of December 25, 1944. Lieutenant Glenn George of the 740th Tank Battalion had seen plenty of abandoned equipment during the German counteroffensive, burned-out trucks, discarded rifles, even a few Panzer IVs with their turrets blown off, but what stood before him now defied logic. A Tiger II, turret number 332, sat motionless on the frozen road, its long 88mm gun barrel pointed uselessly toward the tree line. The tank showed no signs of combat damage. No shell holes pockmarked its massive flanks. No fire had blackened its engine deck. It simply sat there, 70 tons of German engineering, silent and still, as if it had decided, on its own, to stop. George approached cautiously, his boots crunching through the snow. He had been briefed on the King Tiger. Every American tanker had heard the stories. Impenetrable frontal armor, a gun that could destroy a Sherman at distances where the German tank appeared as little more than a dark shape against the horizon. The Tiger II represented the pinnacle of armored warfare, a machine so formidable that Allied intelligence had warned crews to avoid direct engagement whenever possible. Yet here it stood, abandoned without a fight, its crew nowhere to be seen. George climbed onto the hull, pulled himself up to the turret, and dropped inside. The interior smelled of oil and cordite, but everything appeared functional. The gun breech was clean, the ammunition racks held shells, the radio equipment sat undamaged. He settled into the driver's position and, after several attempts, coaxed the massive Maybach engine to life. The tank lurched forward. George drove it perhaps half a kilometre before the fuel gauge confirmed what he already suspected. The Tiger had run out of gasoline. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. This moment, a junior American officer commandeering an abandoned German superweapon that had simply run dry, would eventually lead to one of the most significant technical revelations of the Second World War. But to understand why Tiger 332 mattered, why its capture represented more than just an intelligence coup, we must first understand the mythology that surrounded the Tiger II and the extraordinary faith the German High Command placed in technical superiority over practical reliability. The Tiger II emerged from a design philosophy that had dominated German armour development since the summer of 1941, when Wehrmacht forces first encountered the Soviet 34 and KV-1 tanks during Operation Barbarossa. German commanders, accustomed to facing lightly armoured French and British tanks, found themselves confronting Soviet machines with sloped armour that could deflect standard German anti-tank rounds. The psychological impact was immediate and profound. Reports from the Eastern Front described German soldiers abandoning their positions at the sight of KV-1 tanks, which seemed immune to the 37mm and 50mm guns then standard in panzer divisions. One famous incident at Raseiniai in Lithuania saw a single KV-1 tank hold up an entire German column for more than 24 hours, surviving multiple direct hits before finally being destroyed by engineers who crawled beneath it to place demolition charges. This encounter catalyzed a shift in German tank design philosophy. If the enemy possessed heavy armor, Germany must build heavier armor. If Soviet guns could penetrate German tanks, German guns must penetrate thicker Soviet armor. The result was an arms race measured in millimeters of steel plate and calibers of main guns. The Panzer III and IV, which had served adequately against French Char B1S and British Matildas, were deemed insufficient. Germany needed heavy tanks, schwer Panzerkampfwagen, capable of dominating the battlefield through sheer material superiority. The Tiger I, introduced in late 1942, represented the first fruits of this philosophy. At 56 tons, mounting an 88mm gun adapted from the legendary Flak 36 anti-aircraft cannon, the Tiger I could destroy any Allied tank at ranges exceeding 2,000 meters. Its frontal armor, 100mm thick and nearly vertical, was impervious to most contemporary Allied anti-tank weapons. Early deployments near Leningrad and in Tunisia demonstrated the Tiger's tactical value. German propaganda seized upon the psychological impact, portraying the Tiger as an unstoppable iron beast that embodied German technical genius. The Tiger IIs' reputation grew not just from its combat effectiveness, but from the mythology surrounding it, a mythology carefully cultivated by the Reich Ministry of Public Enlightenment and Propaganda, which understood that weapons could serve psychological purposes as much as tactical ones. But even as the Tiger I entered service, German engineers recognized its limitations. The vertical armor, while thick, was less efficient than sloped armor, which increased effective thickness by forcing projectiles to penetrate at an angle. The interleaved road wheel system, designed to distribute the tank's weight, proved maintenance-intensive and prone to mud accumulation, which would freeze solid in Russian winters. Most critically, the Tiger II's weight strained existing bridges, required specialized transport equipment, and limited its operational mobility. These concerns led to design studies for a more advanced heavy tank that would incorporate the lessons learned from the Tiger I while addressing its weaknesses. The Tiger II program began in earnest in January 1943, with design contracts awarded to both Henschel und Sohn and Porsche KG. The specification called for a tank that would combine the Tiger II's firepower with improved armor protection and better tactical mobility. The gun would be upgraded to the longer 88mm Quay 43L71, with a barrel measuring over 6 meters long and capable of penetrating 185mm of armor at 1,000 meters. The armor scheme would adopt the sloped design pioneered by the Soviet 34, with frontal hull armor 150mm thick, set at an optimal angle to maximize effective thickness. The result would be a tank whose frontal arc was effectively invulnerable to every Allied tank gun then in service or development. Henschel's design, ultimately selected for production, incorporated a hull layout similar to the Panther tank, with sloped front armor and a rear-mounted engine. The suspension used overlapping road wheels mounted on torsion bars, a refinement of the Tiger I's system that eliminated the full, interleaving arrangement while maintaining good ground pressure distribution. The turret, designed by Krupp, was a massive cast and welded structure with frontal armor 185mm thick and a distinctive curved front that gave the Tiger II its characteristic profile. When the first production models emerged from the Henschel plant at Kassel in January 1944, they represented, on paper, the most formidable tank ever built. The specifications seemed to justify German confidence. The Tiger II weighed approximately 70 tons in combat configuration, 14 tons heavier than the Tiger I, and more than twice the weight of the most common American tank, the M4 Sherman. Its main armament, the 88mm KWK-43, could fire armor-piercing rounds at a muzzle velocity of 1,000 meters per second, giving it the ability to penetrate the frontal armor of a Sherman at ranges exceeding 3,000 meters, well beyond the effective range of the Sherman's 75mm or even 76mm guns. Against the Tiger II's frontal armor, Allied tankers faced a desperate equation: close to within 300 meters for a slim chance at a penetrating hit, while remaining within the Tiger's kill zone for the entire approach. The Tiger II's combat debut came in July 1944, when the 503rd Heavy Panzer Battalion received 14 of the new tanks and deployed them to Normandy. On July 18th, these Tigers engaged Canadian forces near Caen in what should have been a demonstration of German armor superiority. Instead, the engagement revealed the first hints of the Tiger II's fundamental problems. 2 of the new tanks were lost before they could effectively engage one to mechanical breakdown, one abandoned when it became immobilized crossing difficult terrain. The remaining Tigers fought well in the tactical sense, destroying several Allied tanks, but the battalion's combat report noted persistent mechanical issues with the final drives and transmission systems that limited the tank's mobility and operational availability. These early problems were attributed to teething issues common to any new weapons system. German engineers assured field commanders that modifications would address the initial reliability concerns. Production continued at a steady pace through the summer and fall of 1944, with the Wehrmacht planning to equip heavy panzer battalions across both the eastern and western fronts with the new supertank. By December, when German forces launched their surprise offensive through the Ardennes forest in what would become known as the Battle of the Bulge, at least 150 Tiger IIs participated in the attack, nearly one-third of total production. This massive concentration of Germany's most advanced armour was intended to spearhead the breakthrough that would split Allied forces, capture the vital port of Antwerp, and potentially force the Western Allies to negotiate a separate peace. The Ardennes offensive placed enormous logistical and mechanical demands on the Tiger II battalions. The densely forested terrain, narrow roads, and winter weather conditions created an environment hostile to heavy armour. Tigers advancing along congested forest roads found themselves unable to manoeuvre around obstacles or execute the kind of sweeping flanking movements that German armour doctrine favoured. The weight that made them nearly invulnerable frontally also made them nearly impossible to deploy effectively. Bridges collapsed under their mass. Road surfaces broke apart beneath their tracks. Most critically, the Tiger II's fuel consumption proved catastrophic. Under ideal road conditions, the tank could travel perhaps 120 kilometers before requiring refueling. Cross-country, fighting through the Ardennes terrain, that range dropped to 80 kilometers or less. Kampfgruppe Peiper, commanded by Obersturmbannführer Joachim Peiper of the 1st SS Panzer Division Leibstandarte Adolf Hitler, included several Tiger IIs in its spearhead force. Peiper's battle group achieved the deepest penetration of the German offensive, advancing nearly 70 kilometers beyond the initial breakthrough point. But even this success was constrained by the limitations of the heavy tanks. Tigers that broke down had to be abandoned. German forces lacked the recovery vehicles capable of towing 70-ton tanks through the muddy forest roads. Tigers that ran out of fuel became roadblocks, forcing lighter vehicles to divert around them or wait while precious gasoline was diverted from other units. The very presence of the Tigers, intended to guarantee German superiority, instead created bottlenecks and complications that slowed the entire offensive. Tiger 332 belonged to this battle group. Its specific combat history during the Ardennes offensive remains partially obscured by the chaos of those December days, but unit records indicate it participated in the attack on Stavelot and the advance toward the Meuse River bridges. At some point during the offensive, likely December 24th or early December 25th, the tank exhausted its fuel supply on the road between Trois-Ponts and Caux. Rather than destroy it, standard procedure, when abandoning equipment to prevent enemy capture, the crew apparently fled in haste, leaving the tank intact. Perhaps they believed German forces would recapture the area. Perhaps they simply lacked the demolition charges necessary to destroy such a massive vehicle. Or perhaps, after days of watching Tigers break down, run dry, and become liabilities rather than assets, they simply abandoned it in disgust. When Lieutenant George discovered the tank on Christmas morning, he made a decision that would prove more consequential than he could have imagined. Rather than report the find and move on, he drove the Tiger, briefly before it ran out of fuel a second time. This act of battlefield improvisation brought the abandoned superweapon to the attention of Colonel Rubel, commanding officer of the 740th Tank Battalion, who immediately recognized its intelligence value. Rubel contacted 1st Army headquarters with a simple message. An intact King Tiger had been captured, and if the Army wanted it for technical evaluation, arrangements needed to be made for its recovery and transport. The recovery operation itself demonstrated the practical challenges the Tiger II posed. The 463rd Ordnance Evacuation Company, tasked with retrieving the tank, required specialized equipment and multiple days to load the 70-ton vehicle onto a reinforced railway flat car. The tank proved too heavy for standard recovery vehicles and too large for standard transport equipment. Eventually, engineers managed to load it, though the process required building temporary ramps and using ceiling, multiple tow vehicles in tandem. The Ordnance Company painted their unit identification 463 ORD EVAC on the turret, and Tiger 332 began its journey to Antwerp, where it would be loaded aboard a ship bound for the United States. The decision to send the Tiger to America, rather than conduct evaluation in the European theatre, reflected the priority Allied intelligence placed on understanding German armour. While Soviet forces had captured several Tiger IIs on the Eastern Front and British forces had examined damaged examples in Normandy, the United States had not yet obtained an intact, fully operational King Tiger for comprehensive testing. Tiger 332, despite its fuel starvation, remained mechanically complete and largely functional. It represented an opportunity to conduct the kind of thorough technical analysis that battlefield conditions rarely permitted. The ship carrying Tiger 332 docked in the United States in early January 1945. From the port, the tank travelled by rail to Aberdeen, proving ground in Maryland, the U.S. Army's primary facility for testing and evaluating weapons systems. Aberdeen Proving Ground had examined numerous German weapons during the war, captured Panzer IVs, Panthers, even a Tiger I, but the arrival of Tiger 332 generated particular interest among the engineers and ordnance specialists. Here was Germany's ultimate answer to Allied armour, the weapon German propaganda had portrayed as invincible, the tank that American crews had been warned could destroy them at ranges where they couldn't effectively fight back. Now it sat in a secure hangar at Aberdeen, waiting to reveal its secrets. The examination team at Aberdeen approached Tiger 332 with a mixture of professional curiosity and practical skepticism. American engineers understood that German manufacturing quality, particularly for complex military equipment, had declined throughout 1944, as Allied bombing destroyed factories, killed skilled workers, and disrupted supply chains for critical materials. They expected to find evidence of this decline shortcuts in manufacturing, substitutions of inferior materials, perhaps signs of sabotage by forced labourers. What they found proved far more illuminating than simple manufacturing defects. The Tiger II's problems were not primarily the result of rushed production or material shortages. They were fundamental design flaws that no amount of careful manufacturing could overcome. The examination began with basic measurements and documentation. Every dimension was recorded. Every component was photographed. The armour was measured at multiple points to verify thickness and angle. The examination team confirmed what intelligence reports had indicated. The Tiger II's frontal armour was indeed extraordinarily thick. The front hull plate measured 150 mm at a well-designed angle that increased effective thickness to nearly 230 mm against projectiles striking perpendicular to the surface. The turret front reached 185 mm in its thickest sections. To put this in perspective, the American 90 mm gun, the most powerful tank weapon in the U.S. arsenal at that time, could penetrate approximately 170 mm of armour at 500 meters under ideal conditions. Against the Tiger II's frontal arc, it had virtually no chance of a killing shot unless circumstances allowed a hit against weaker side or rear armour. The 88 mm KWK-43 gun received equally thorough examination. The barrel alone weighed approximately 1 ton and stretched over 6 meters in length. The breech mechanism, while similar to the earlier KWK-36 used in the Tiger I, incorporated refinements that improved rate of fire and simplified ammunition handling. Test firing conducted at Aberdeen's artillery range using captured German ammunition confirmed that the gun's ballistic performance matched German specifications. At 1,000 meters, the armour-piercing round could penetrate 185 mm of armour plate. At 2,000 meters, it still retained sufficient energy to penetrate 150 mm. For comparison, the Sherman's frontal armour measured 63.5 mm, and even the heavily armoured M26 Pershing, just beginning to reach Europe in limited numbers, had only 100 mm of frontal armour. The Tiger II could destroy any American tank at ranges approaching 3,000 meters. The fire control system impressed the American examiners. The Turmszielfernrohr 9 binocular gun sight provided excellent optical clarity and accurate range estimation capabilities. The turret traverse mechanism, electrically powered with manual backup, allowed smooth tracking of targets. The gun mounting system incorporated a balance mechanism that reduced the physical effort required to elevate or depress the massive gun tube. In terms of gunnery, the Tiger II represented sophisticated engineering that gave it significant advantages in tank versus tank combat. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But as the examination team moved beyond measuring armor and testing guns, they began uncovering the fundamental problems that had plagued the Tiger II since its introduction. The powertrain examination revealed issues that no amount of skilled gunnery could overcome. The Tiger II used the Maybach HL230P 30V12 engine, an improved version of the HL210 used in the Tiger I. This engine produced approximately 700 horsepower at 3,000 revolutions per minute, impressive for the era, but woefully inadequate for the Tiger II's 70-ton mass. The power-to-weight ratio worked out to exactly 10 horsepower per ton, compared to 13.8 horsepower per ton for the Tiger I and approximately 15 horsepower per ton for the Sherman M4A3. In practical terms, this meant the Tiger II struggled on any significant incline, accelerated slowly, and placed enormous stress on every component of the drivetrain, simply trying to move its own weight. The transmission analysis proved even more revealing. The Tiger II used the Maybach Olvar OG 4012-16 Model B transmission, providing 8 forward gears and 4 reverse gears. This transmission, while sophisticated in design, was already operating at its design limits in the 45-ton Panther tank. In the 70-ton Tiger II, it was chronically overstressed. The examination team found evidence of this stress throughout the transmission assembly. Gear teeth showed wear patterns consistent with operating under excessive load. Bearing surfaces displayed signs of overheating. The clutch plates, particularly the steering clutches, showed premature wear that American engineers attributed to the enormous effort required to turn 70 tons of tank. Interrogation of captured German tankers confirmed what the physical evidence suggested. Tiger II drivers had to exercise extreme care with the steering system, making gradual turns and avoiding sharp maneuvers that could overheat or damage the clutches. In combat situations requiring rapid position changes, this limitation could prove fatal. The final drive examination revealed the Tiger II's most critical mechanical weakness. The final drive, which connects the transmission to the drive sprockets that turn the tracks, represented the last link in the power delivery chain and bore the full mechanical stress of moving the tank's mass. In the Tiger II, the final drives used a planetary gear system designed to provide the necessary gear reduction while fitting within the limited space available in the hull. Under laboratory conditions, with proper maintenance and moderate use, these final drives might have proven adequate. Under battlefield conditions, they failed with alarming frequency. The examination team found that the roller bearings supporting the drive bar were inadequately sized for the loads they experienced. Metal fatigue was visible in components that, theoretically, should have lasted the tank's entire service life. American engineers calculated that under hard-use cross-country movement, frequent direction changes, operation in muddy or soft ground, the final drives could be expected to fail after as little as 150 to 200 kilometers of operation. This figure, 150 kilometers, would become the informal measure of the Tiger II's reliability problem. While individual tanks might exceed this distance, and some German units reported examples that travelled significantly farther without major breakdown, the average operational range, before requiring major repair work, hovered around this distance. For context, the Sherman M4A3, the most common late-war American tank, could routinely operate for 1,500 to 2,000 kilometers between major overhauls. Soviet 34 tanks, despite their reputation for crude manufacturing, typically managed 1,000 to 1,500 kilometers. The Tiger II's operational radius was an order of magnitude worse than its opponents, not because of enemy action but because of fundamental design limitations that no amount of field-expedient repairs could overcome. The examination team at Aberdeen documented all of these findings in detailed technical reports that circulated among Allied intelligence agencies and informed tactical doctrine for units likely to encounter Tiger IIs. But the reports went beyond mere technical specification. They included assessments that revealed American engineers' recognition that the Tiger II represented a profound misunderstanding of what made an effective weapons system. One report noted that the Tiger II's designers had optimized for a single scenario, the long-range tank versus tank duel, while neglecting the operational realities that determined whether a tank could reach the battlefield, sustain combat operations, and remain available for future engagements. The German engineers, brilliant as they were in matters of armor and ballistics, had failed to grasp that reliability and maintainability were not secondary characteristics but fundamental requirements. This realization that technical sophistication could become a liability if it compromised practical utility would inform American armored vehicle development for decades after the war. The M26 Pershing rushed into service in early 1945, specifically to counter the Tiger II, deliberately prioritized mechanical reliability over maximum armor protection. Its designers recognized that a tank that could consistently reach the fight and remain operational was worth more than a tank that might win any individual engagement but would spend half its time under repair. This philosophy would continue through the M46, M47, and M48 Patton series, eventually culminating in the M60 and M1 Abrams, both of which embodied the principle that operational availability mattered as much as combat capability. Meanwhile, on the Eastern Front, Soviet forces were conducting their own examination of captured Tiger IIs and reaching remarkably similar conclusions. In August 1944, Red Army units captured 2 intact Tiger IIs near Sandomierz, Poland, during the Lvov-Sandomierz offensive. These tanks, fresh from recent combat, were immediately transported to the Soviet testing grounds at Kubinka, near Moscow. The journey itself proved illuminating. Despite traveling primarily by rail, both tanks suffered multiple mechanical breakdowns during the relatively short trip. The detailed Soviet examination reports, declassified decades after the war, revealed problems that closely paralleled American findings. The Soviet test crews' experiences provided vivid illustration of the Tiger II's mechanical fragility. During initial test drives in late August, conducted in the unusually hot summer weather that year, the cooling system proved inadequate. The Maybach engine, struggling to move 70 tons through the soft ground of the Proving Ground test course, generated heat faster than the cooling system could dissipate it. Within an hour of operation, temperature gauges showed the engine overheating. Continued operation caused the transmission oil to thin, reducing its lubricating properties and accelerating wear on gear, teeth, and bearings. The gearbox began to fail. Soviet mechanics, documenting every detail, noted that the cooling system's design appeared adequate for moderate European climates, but entirely insufficient for the temperature extremes of the Eastern Front, where summer temperatures could exceed 35 degrees Celsius and winter temperatures could drop below -30. The suspension system presented its own challenges. The Soviet test course included rough terrain, ditches, and obstacles designed to stress-test armored vehicles under conditions approximating combat. The Tiger II's overlapping road wheel system, while distributing weight effectively, proved vulnerable to mud accumulation and track damage. More critically, the torsion bars that provided suspension for the road wheels were stressed near their design limits by the tank's weight. After less than 100 kilometers of test driving, which included numerous stops, starts, and direction changes, the left front torsion bar fractured completely. Soviet metallurgical analysis of the failed bar revealed stress patterns suggesting that the bars were operating at or beyond their fatigue limit under normal usage. The implication was clear. The Tiger II's suspension was a wear item, requiring frequent replacement of components that should have been durable enough to last thousands of kilometers. The final drive failures experienced by the Soviet test tank mirrored what American engineers would later find. During mobility trials, which aimed to determine maximum speed, acceleration, and handling characteristics, the right final drive jammed after the tank had traveled approximately 444 kilometers, according to its own speedometer. Soviet mechanics disassembled the final drive housing and found the drive bar roller bearing completely destroyed. Metal fragments from the failed bearing had contaminated the gear oil and caused secondary damage to other components. The mechanics replaced the failed final drive with the unit from the second captured Tiger, which had suffered different damage and could serve as a parts source. The replacement allowed testing to continue, but after completing the mobility trials, another 113 kilometers of operation inspection revealed that the replacement final drive was also failing, with the same bearing showing early signs of the metal fatigue that would lead to complete failure. The Soviet testing report's conclusion was damning. Inspection of the final drives shows that their drive bar bearing design is unreliable. This was not a problem that could be fixed with better manufacturing quality or more skilled crews. It was a fundamental design flaw. The final drives were simply inadequate for the loads they experienced, and no amount of careful operation could prevent eventual failure. Soviet engineers calculated that under typical combat conditions, cross-country movement across varied terrain, frequent position changes, the operation by adequately trained but not expert crews, the final drives could be expected to fail every 100 to 150 kilometers. For a tank intended to conduct offensive operations, this meant that a Tiger II unit could barely advance 1 day's worth of tactical movement before tanks would begin breaking down and requiring recovery. The implications of these findings extended far beyond technical specifications. Both American and Soviet intelligence analysts recognized that the Tiger II's mechanical limitations fundamentally altered its tactical value. A tank that required major maintenance every 150 kilometers was not a weapon of offensive warfare. It was, at best, a mobile pillbox suitable only for defensive positions within easy reach of depot-level maintenance facilities. For a nation like Germany, in late 1944 and early 1945, fighting on two fronts with collapsing logistics and fuel supplies, deploying Tiger IIs represented a massive misallocation of scarce resources. The mathematics told a devastating story. Each Tiger II required approximately 300,000 man-hours to manufacture, compared to roughly 10,000 man-hours for a Sherman or 15,000 for a 34. The steel required for one Tiger II could produce roughly 3 Panthers or 5 Panzer IVs. The skilled labor pulled from other war industries to build Tiger IIs represented a permanent reduction in Germany's ability to manufacture trucks, aircraft, artillery pieces, or any of the thousands of other items a modern military required. And for what? A tank that, statistically, would break down before it travelled the distance from Berlin to Hamburg. A tank that consumed so much fuel that even reaching a battlefield 100 kilometers away required logistical support that Germany could rarely provide by 1945. German field commanders, dealing with these realities daily, recognized the problem even if the High Command refused to acknowledge it. Unit war diaries from Tiger II battalions in early 1945 paint a grim picture of operational reality. The 500 1st Heavy Panzer Battalion's records for January 1945 note that of 45 Tiger IIs nominally assigned to the unit, an average of only 26 were operational on any given day. The remaining 19 sat in various states of disrepair, waiting for spare parts that rarely arrived, or for specialized maintenance that required transporting the tanks back to depot facilities. But transporting a 70-ton tank required heavy-duty railway cars, which were increasingly scarce as Allied air power systematically destroyed German rolling stock. Tanks that broke down in forward positions often had to be abandoned and destroyed by their own crews simply because recovery was impossible. The 500 3rd Heavy Panzer Battalion, which had first deployed Tiger IIs in Normandy, reported similar problems through the fall and winter of 1944. A report from November of that year, after operations in Hungary, noted that while the Tiger IIs performed well in defensive ambush positions where they could use their superior gun range, any operation requiring movement of more than 50 kilometers resulted in significant breakdowns. The report specifically mentioned final drive failures as the primary mechanical problem, noting that crews had learned to make gradual turns and avoid sudden direction changes to reduce stress on the drives, but that combat rarely allowed for such careful maneuvering. Perhaps the most telling statistic came from a March 1945 summary of German armoured vehicle operational rates. This document, captured after the war and examined by Allied intelligence, showed that 59% of Tiger IIs were operationally ready at that point, a figure that sounds dismal until compared to the 48% operational rate for Panther tanks or the 62% rate for the much simpler Panzer IV. The Tiger II's reliability had actually improved from its disastrous early showing, as Henschel engineers made modifications to address the most critical problems and field crews became more skilled at maintaining the temperamental machines. But even this improved reliability was worse than that of a design dating from 1936. The Tiger II's sophistication had become its curse. The fuel consumption issue compounded every other problem. The Tiger II's Maybach HL230 engine, already underpowered for the tank's weight, achieved abysmal fuel efficiency. Under ideal road conditions, driving at optimal cruising speed on level ground, the tank consumed roughly 500 litres of gasoline per 100 kilometres. Cross-country, that figure rose to 700 litres or more. The tank's fuel capacity was approximately 800 to 60 litres, giving it a theoretical range of 100 to 20 kilometres on roads, assuming perfect conditions, no combat manoeuvring, and no extended idling. In reality, combat operations rarely allowed for optimal fuel economy. Tigers, advancing to contact, manoeuvring for position, reversing to avoid threats, or simply idling with engines, running to keep electrical systems and heaters operational, consumed fuel at rates that could reduce effective range to 80 kilometers or less. For context, a Sherman M4A3 consumed approximately 250 liters per 100 kilometers under similar conditions and carried 625 liters of fuel, giving it a range of approximately 250 kilometers. It could travel twice as far on less than half the fuel. More critically, it could be refueled from standard jerry cans that any supply vehicle could carry. The Tiger II required special fueling equipment and enormous quantities of gasoline that had to be diverted from other vehicles. In an army increasingly starved for fuel, Germany's synthetic fuel production dropped by 60% between May and September. 1944, due to Allied bombing, the Tiger II's thirst became an operational impossibility. The Battle of the Bulge illustrated these problems at strategic scale. German planning for the Ardennes offensive allocated fuel based on optimistic assumptions about capturing Allied supply dumps. The plan required armoured spearheads to advance approximately 100 kilometres in the first 48 hours, crossing the Meuse River before Allied reserves could react. This timeline was achievable for Panzer IVs, marginally possible for Panthers, and completely unrealistic for Tiger IIs. The heavy tanks, advancing through the narrow forest roads of the Ardennes in winter conditions, consumed fuel at their highest rates while making minimal progress. Kampfgruppe paper, whose Tiger IIs included the tank that would become Tiger 332, managed to advance approximately 70 kilometers before fuel shortages, mechanical breakdowns, and stiffening Allied resistance halted the attack. The fate of Kampfgruppe paper's Tiger IIs exemplified the broader pattern. Several broke down during the advance and had to be destroyed by their crews. Others reached defensive positions around the town of La Glaise, where they fought effectively in the exact scenario the Tiger II was designed for: static defensive firing from concealed positions against Allied armour, attempting to advance along predictable routes. One Tiger, turret number 213, successfully engaged American tanks and tank destroyers, its thick armour deflecting multiple hits, while its gun destroyed several Allied vehicles. But when the American forces encircled La Glaise and Paper, ordered a retreat, the Tiger IIs became liabilities. With insufficient fuel to drive back through enemy-held territory and no possibility of recovery, they had to be abandoned. Tiger 213 sits in La Glaise to this day, a permanent monument to the offensive that failed. Its muzzle brake was shot away during the fighting, and a 90mm shell from an American tank destroyer crippled its right drive sprocket, one of the few areas vulnerable to Allied weapons, but the tank's ultimate fate was determined not by enemy fire but by empty fuel tanks. Tiger 332's abandonment on the road to Koo followed the same pattern. Unit records suggest it participated in fighting around Stavelot before advancing toward the Meuse. At some point, likely during the general German withdrawal that began in late December, it exhausted its fuel supply and could not be recovered. The crew faced a simple calculation: destroy the tank to prevent capture, or flee, and hope German forces would recapture the area before the Americans discovered it. They chose the latter, a decision that ultimately delivered one of Germany's most advanced weapons intact into enemy hands for comprehensive examination. The strategic consequences of the Tiger II program extended beyond the immediate waste of resources. Every Tiger II built represented an opportunity cost, what Germany could have produced instead with the same resources. The 300,000 man-hours required to build one Tiger II could have produced approximately 30 Sturmgeschütz 3 assault guns, which, while less capable in tank versus tank combat, proved far more versatile and reliable in the defensive warfare Germany was forced to conduct by 1944. The steel that went into one Tiger II could have built 5 Panzer IVs, which, while outclassed by Allied heavy tanks, were mechanically mature, reasonably reliable, and sufficient for infantry support and exploitation roles. Most critically, the resources devoted to Tiger II production could have been allocated to trucks, half-tracks, and other logistics vehicles that would have improved Germany's ability to supply and support the forces it already had. German industrial planning in the final years of the war suffered from a fundamental disconnect between Adolf Hitler's vision of warfare and the material realities his generals faced. Hitler believed that technological superiority manifested in superweapons like the Tiger II, the V-2 rocket, and the Me-262 jet fighter could compensate for Germany's declining industrial capacity and manpower. He envisioned wonder weapons that would shock and demoralize the Allies, forcing them to negotiate rather than continue the costly advance into Germany. This vision ignored the basic arithmetic of industrial warfare: that reliable, mass-produced weapons, supported by robust logistics, would always defeat superior, but scarce and fragile weapons that broke down before reaching the battlefield. The Tiger II epitomized this disconnect. It was designed for a war of maneuver and decisive armored engagements, a war that had ended for Germany after the failure at Kursk in the summer of 1943. By the time Tiger IIs entered service in mid-1944, Germany was fighting a defensive war of attrition on multiple fronts, a war where operational mobility and sustainability mattered more than winning individual tank duels. The Tiger II excelled at the latter while failing at the former. It was a brilliant answer to the wrong question, a masterpiece of engineering applied to a problem that no longer existed. The human cost of this miscalculation is difficult to quantify but impossible to ignore. Each Tiger II required a crew of 5, highly trained men, a tank commander, gunner, loader, driver, and radio operator. These men received extensive, specialized training on the Tiger II's complex systems. They represented a significant investment of time and expertise. When a Tiger II broke down far from friendly lines and had to be abandoned, as happened repeatedly throughout 1945, these skilled crews often had to retreat on foot through enemy-held territory or be captured. The Wehrmacht could ill afford to lose experienced armoured crews to mechanical failures rather than combat losses. Moreover, the psychological impact on German tankers cannot be dismissed. Crews who had been told they were receiving the 10 most advanced tank in the world, a weapon that would guarantee their superiority over Allied armour, instead found themselves nursing temperamental machines that broke down with alarming regularity. They learned to fear cross-country movement not because of enemy ambush, but because rough terrain would stress the final drives. They had to constantly monitor engine temperatures, transmission behavior, and fuel consumption, rather than focusing on tactical awareness. The confidence that a reliable weapon system provides the knowledge that your equipment will perform as expected when needed was absent. Instead, Tiger II crews operated with the gnawing uncertainty that their tank might break down at the worst possible moment, stranding them in enemy territory. The contrast with Allied tankers' experience illuminates the practical value of reliability over technical sophistication. American Sherman crews certainly feared encountering Tigers. The Sherman's vulnerability to the German 88mm gun was well known and produced understandable anxiety. But Sherman crews also knew that their tanks would start reliably, would not break down during an advance, and could be maintained and repaired by unit mechanics without requiring specialized equipment or factory-level expertise. They trusted their equipment, even while recognizing its limitations. This trust translated into operational effectiveness that no amount of armor, thickness, or gun performance could replicate. Soviet tanker memoirs from the war's final months note a similar evolution in attitudes toward German armor. Early in the war, Tigers had inspired genuine fear, bordering on panic. By 1945, experienced Soviet crews recognized Tigers as dangerous but manageable threats. They understood that Tigers were increasingly rare, often immobile due to mechanical problems or fuel shortages, and could be defeated through combined arms tactics even if direct frontal engagement remained. Suicidal. The psychological dominance the Tiger I had achieved in 1942 and 1943 had evaporated by the time the Tiger II entered service, not because Allied tanks had become significantly more capable, but because the mystique of German technical invincibility had been shattered by the reality of mechanical fragility. The final chapter of the Tiger II story played out in the spring of 1945, as Soviet forces closed on Berlin from the east and American, British, and Canadian forces advanced from the west. Remaining Tiger II units were deployed in desperate defensive actions, often in static positions where their mobility problems were less critical and their firepower could be fully utilized. Some scored impressive tactical successes. The 503rd SS Heavy Panzer Battalion claimed approximately 500 Allied tank kills between January and April 1945 on the Eastern Front, an extraordinary achievement if the numbers are accurate. But these tactical successes occurred within the context of strategic collapse. For every Allied tank destroyed, Germany was losing ground, resources, and irreplaceable trained personnel at rates that no amount of tactical success could offset. The loss rate for Tiger IIs in these final months tells the story. The 503rd lost 45 Tiger IIs between January and April, nearly its entire strength, but combat damage accounted for only a minority of these losses. Most were abandoned and destroyed by their crews after mechanical breakdowns or when fuel supplies were exhausted. As Soviet and Allied forces overran German positions, they found Tiger IIs scattered across the landscape, many intact, simply out of fuel or immobilized by final drive failures. The tank designed to be invulnerable was defeated not by superior enemy weapons, but by the mundane realities of logistics and mechanical engineering. When the war in Europe ended on May 8, 1945, fewer than 50 Tiger IIs remained in German hands, and virtually none were operational. The survivors sat in depot yards or had been abandoned during the final retreats. Allied forces captured or destroyed the remaining examples, adding to the collection of Tiger IIs already in Allied hands for technical evaluation. The total production run of 492 tanks represented less than 1% of German armoured vehicle production during the same period, but the resources devoted to the Tiger II program, the engineering hours, the manufacturing capacity, the raw materials had been diverted from other priorities that might have extended German resistance or at least reduced the catastrophic human cost of the war's final months. The post-war fate of Tiger 332 reflects the broader historical trajectory of German superweapon programs. After its examination at Aberdeen Proving Ground, the tank was displayed outdoors for nearly 40 years, painted in a silver-grey colour that bore no resemblance to its wartime camouflage. Exposed to Maryland's weather, the tank slowly deteriorated. Rust spread across surfaces that had once been impervious to enemy fire. The rubber portions of the road wheels cracked and rotted. The sophisticated optical equipment and mechanical systems that American engineers had carefully documented gradually degraded into inoperable relics. In the 1980s, the tank was transferred to the Patton Museum of Cavalry and Armor at Fort Knox, Kentucky, where conservators partially restored it and cut away one side of the hull to display the internal layout for educational purposes. This modification, slicing open the hull to show the engine, transmission, and drive systems, transformed Tiger 332 from a weapon into a teaching tool. Museum visitors can see precisely why the Tiger II failed. The massive engine crammed into inadequate space, the stressed transmission components, the complex final drive assembly that proved so unreliable. The cutaway view illustrates the fundamental problem more clearly than any technical report. The Tiger II was overbuilt in some areas, particularly armor and firepower, and underbuilt in others, particularly the powertrain. German engineers had optimized for a single characteristic, combat effectiveness in direct engagement, while neglecting the systems that determined whether the tank could reach and sustain combat operations. The surviving Tiger IIs, scattered in museums across the world, serve similar educational purposes. The example at the Musée des Blindés in Saumur, France, the only remaining operational Tiger II, can be started and driven short distances under carefully controlled conditions. But even this meticulously maintained museum piece requires constant attention from skilled mechanics, using specialized tools and parts. The tank at Kubinka in Russia, one of the examples captured and tested in 1944, stands as a monument to Soviet testing that revealed the Tiger II's flaws. Each survivor tells the same story. Technical sophistication, divorced from practical reality, produces impressive but ultimately ineffective weapons. The lessons from the Tiger II program influenced post-war armored vehicle development in both obvious and subtle ways. American designers, working on what would become the M46, M47, and M48 Patton tanks, explicitly prioritized mechanical reliability and ease of maintenance, alongside combat capability. The M48, which entered service in the early 1950s, deliberately used a powerful engine relative to its weight, approximately 20 horsepower per ton, ensuring adequate power reserves for the transmission and final drives, even under high-stress conditions. Its designers had learned from examining Tiger 332 and other captured German armor that understressing mechanical components, even at the cost of some size or weight penalty, produced more operationally effective vehicles than overstressing components to save space or weight. Soviet designers drew similar lessons. The T-54, which became the Soviet Union's main battle tank in the late 1940s and remained in production for decades, embodied a philosophy antithetical to the Tiger II. Rather than maximize armor and firepower at the expense of mobility and reliability, the T-54 balanced all characteristics at moderate levels. Its armor was sufficient to protect against most contemporary weapons, but not excessive. Its gun was powerful enough to engage enemy armor effectively, but not so large that it compromised the tank's other characteristics. Its engine and transmission were conservatively rated, ensuring long service life and high operational availability. The T-54 could not dominate any individual engagement the way a Tiger II theoretically could, but it could reliably reach the battlefield, sustain prolonged operations, and remain in service for decades with minimal modification. Even Germany, in its post-war reconstruction, applied the Tiger II lessons. The Leopard 1, West Germany's first indigenous post-war main battle tank design that entered service in the 1960s, represented a complete philosophical break from Tiger II thinking. Rather than emphasize armor, which had been the defining characteristic of German heavy tank design, the Leopard 1 prioritized mobility, firepower, and crew survivability through other means. It was relatively lightly armored by the standards of its era, but fast, reliable, and easy to maintain. German engineers, having witnessed the Tiger II's failure firsthand, designed the Leopard to be exactly what the Tiger II was not: a practical, sustainable weapon system that could be produced in adequate numbers, maintained by average technicians, and operated effectively under field conditions. The Tiger II's influence extended beyond tank design into broader military procurement philosophy. The requirements creep that plagued the Tiger II program, the tendency to add capabilities and increase specifications until a weapon system becomes so complex and expensive that it defeats its own purpose, became a recognized danger in post-war defense planning. Military theorists identified the Tiger II, along with other German wonder weapons like the V-2 rocket and Me-262 jet, as cautionary examples of what happens when technical perfection becomes the enemy of operational adequacy. The phrase, perfect, is the enemy of good enough, gained currency in military circles, often explicitly referencing the Tiger II program as the paradigmatic failure case. The human dimension of the Tiger II story, men like Lieutenant Glenn George and the countless tank crews on all sides who encountered these massive machines, deserves final consideration. George's decision to climb into that abandoned Tiger on Christmas morning 1944 was motivated by soldiers' curiosity and tactical opportunism, not historical consciousness. He could not have known that his brief drive in Tiger 332 would contribute to one of the war's more significant intelligence coups. The tank's journey from a frozen Belgian road to Maryland to Kentucky traces a path from active weapon to historical artifact, from feared enemy equipment to educational tool. George himself survived the war and lived to see Tiger 332 in its museum setting, a monument to German engineering ambition and American practical analysis. The German crews who manned Tiger IIs deserve recognition for their courage and skill, even as we acknowledge the flawed weapon system they were asked to operate. They trained extensively on complex machinery, maintained it under impossible conditions, and fought with it despite knowing its limitations. When they abandoned Tiger 332 near Koo, they were making a practical decision in desperate circumstances, not committing an act of cowardice or neglect. The tank had become a liability rather than an asset, consuming fuel the unit needed for withdrawal, while offering no prospect of contributing to the defense. Their choice to flee rather than destroy it may have been hasty, but it was understandable given the chaos of the Ardennes offensive's collapse. The Soviet test crews at Kubinka, who documented the Tiger II's mechanical failures with such meticulous detail, performed invaluable service, not just for their own army, but for military historians decades later. Their reports, preserved in Soviet archives and eventually translated and published, provide the most comprehensive documentation of the Tiger II's operational problems under controlled conditions. These men approached their examination with professional rigor, neither exaggerating problems to make German equipment appear inferior, nor minimizing them out of respect for enemy engineering. They simply recorded what they observed. A tank that looked fearsome, performed impressively in gunnery trials, and broke down with depressing regularity under normal operating conditions. The American engineers at Aberdeen Proving Ground who examined Tiger 332 brought their own professional perspective to the task. Unlike frontline troops, who experienced German armour as a tactical threat to be defeated or avoided, the Aberdeen team could analyse the Tiger II dispassionately. Their reports acknowledged the tank's strengths, genuinely formidable armour and firepower, while documenting its weaknesses with technical precision. They recognized that the Tiger II represented skilled engineering applied to flawed specifications, and their analysis influenced not just immediate tactical doctrine, but long-term American armored vehicle development. The lessons learned from Tiger 332 shaped American tank design for the next 2 decades. The profound irony of the Tiger II program, that the tank designed to be invincible was defeated primarily by its own mechanical inadequacy, speaks to fundamental truths about military effectiveness that transcend the specific historical moment. Superior technology matters, but only if that technology can be fielded in adequate numbers, sustained under operational conditions, and employed effectively by the forces using it. A tank that excels in one scenario while failing in all others is not a superweapon. It is a liability dressed in impressive specifications. The Wehrmacht would have been better served by additional Panthers, which, while flawed themselves, were more reliable and versatile, or by increased production of trucks and logistics vehicles that would have improved the mobility and sustainability of existing forces. Germany's commitment to the Tiger II in 1944 and 45 represented a failure of strategic vision that no amount of tactical success could redeem. Adolf Hitler's faith in wonder weapons, in the belief that technical superiority alone could reverse military fortunes, ignored the material realities of industrialized total war. By the time Tiger IIs entered service, Germany had already lost the strategic initiative on both fronts. No tank, however formidable, could compensate for inadequate fuel supplies, disrupted logistics, outnumbered forces, and the overwhelming industrial capacity of the Allied coalition. The Tiger II program diverted scarce resources toward producing a small number of sophisticated tanks that would have marginal strategic impact while consuming resources that might have been better employed elsewhere. The story that began with Lieutenant George discovering an abandoned Tiger on a Belgian road thus ends with a broader meditation on the nature of military power and the dangers of technological fetishism. The Tiger II was not defeated because Allied tanks were better in direct combat. They generally were not. It was defeated because it embodied a philosophy of warfare that prioritized individual combat superiority over operational sustainability. The Allies, particularly the Americans, embraced the opposite philosophy: produce reliable, maintainable weapons in overwhelming numbers, support them with robust logistics, and trust that operational availability would prove more valuable than technical sophistication. This approach, while less glamorous than designing superweapons, proved devastatingly effective. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.